All right, so this is 7.3.1, Coulombs Law. So we're starting electric fields now, and you're going to see that electric fields and gravitational fields are almost identical in many ways, and there are very few differences between them. So if you know gravitational fields very, very well, which you should know at this point, then electric fields are going to be very easy for you. So let's start with 2-point charges, just like how we did in gravitational where we had 2-point masses. So in this case, we're going to have 2-point charges, Q1 and Q2. And at the moment, I'm not going to care about whether they're positive, negative, or their magnitudes. We just know that there's 2-point charges. And from key stage 3 and key stage 4, you should know that if you have 2 or more charged objects, they're going to interact with each other, and they're going to experience some force. So Coulomb's law, very similar to Newton's law of gravitation, says the following. It says that the force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of separation. So definition is almost identical. So if you've memorized one, you've automatically memorized both. Now, using that definition, we're going to construct an equation by considering the diagram above where you have Q1 and Q2. So, we're going to read through the definition and we're going to use that to construct a mathematical relationship. So the force between 2-point charges is directly proportional, so I'm going to put a proportionality symbol. So force is proportional to the product of the charges. Product means multiply them together, so Q1, Q2. And inversely proportional to the square of separation. Separation we denote as R, so square of separation is R squared. So inversely proportional to R squared. So we've got F is proportional to Q1, Q2 over R squared. Now that looks very similar. Should remind you from Newton's law of gravitation, F is proportional to M1, M2 over R squared. Now we don't like proportionality symbols, so we're going to get rid of it and put a constant of proportionality in its place. So we say that F is equal to some constant multiplied by Q1, Q2 all over R squared. And through experimentation and derivation, so you can get this constant through both ways, we find that K is equal to 1 over 4 pi epsilon naught. Epsilon naught is a constant that I'll give to you. So we'll write here K equals to 1 over 4 pi epsilon naught. And now we can put those together to make the equation that you need to learn, which is F is equal to Q1, Q2 over 4 pi epsilon naught R squared. Epsilon naught is called the permittivity of free space. Oops, too many E's. Which is equal to 8.85 times 10 to the minus 12 farads per meter. So permittivity of free space relates to how easy it is or relates to the electric field component of EM waves in a vacuum. And you have another one called the permeability of free space, which relates to the magnetic field component. Essentially. Essentially.
It's always the same.
What?
It's always the same.
What?
The permittivity of free space.
Yes, it's a constant. All right, let's do an example. So calculate A, the electric force between a proton and electron in a hydrogen atom. B, the gravitational force between them. And C, the ratio of the electrostatic force over the gravitational force. You can pause the video here to attempt these questions and then resume the video to see the working out.
Say for instance the question was asked you to work out the resultant force between like two electrons, let's say. Would you have to work out the electric?
Just use that equation.
But would you have to also work out the gravitational force between?
Just use that equation. You're going to see why when we do this example.
Q1, not for A, sir. Q1 and Q2 will be the...
I'm going to solve it now.
But we charge a proton, we charge electron, right?
Yeah. Right. Let's go through the solutions. So in part A, we want the electric force between a proton and electron in a hydrogen atom. So first, we need to think about what atoms are. So here's a hydrogen atom with your one proton and your electron. And we know that an atom is in the order of magnitude of 10 to the minus 10 meters. So we need to make some assumption here and say that the diameter of this atom is just 1 times 10 to the minus 10. It's not the exact value, but the assumption is fine because we're just looking for a ballpark figure. So that means that the separation is going to be roughly equal to 0.5 times 10 to the minus 10 meters for a radius. And then we know that the charge of an electron, so Q of E, is equal to minus 1.6 times 10 to the minus 19 coulombs. And we know that the charge of the proton is equal to 1.6 times 10 to the minus 19 coulombs. For the next question, because we're talking about gravitational fields, we're going to need to know the masses as well. So I'm just going to write these down now before I start solving each question. So just so I have all my values ready. So the mass of an electron is equal to 9.11 times 10 to the minus 31 kilograms. And the mass of the proton is equal to 1.67 times 10 to the minus 27 kilograms. Right. So now let's start solving them. So for part A, we use F equals to Q1, Q2 over 4 pi epsilon naught r squared. Let's put our values in. We don't care about the positive and negative because I'm just looking for the magnitude at the moment. So I'm not going to put the negative sign for the charge of the electron. So we're going to do 1.6 times 10 to the minus 19 times by 1.6 times 10 to the minus 19. So I'll just put squared all over 4 pi times by 8.85 times 10 to the minus 12 times by the radius squared, which is 0.5 times 10 to the minus 10, put brackets around that, and square it. Can you just type that into your calculator and give me the value? It's 9.2 times 10 to the minus 8 newtons. All right. Then for part B, we're going to work out the gravitational force between them. So we do F equals to G m1 m2 all over r squared. So F is equal to, value of G is? 6.67 times 10 to the minus 11 times by m1, so 9, oh, we glitched out there. (9.11) times 10 to the minus 31 times by 1.67 times 10 to the minus 27 all over r squared, so 0.5 times 10 to the minus 10 squared. So F is equal to 4.1 times 10 to the minus 47 newtons. So now, this is going to answer one of your questions, is when you're working out the resultant force, do you also have to work out the gravitational force between them and sum them up? Well, look at the order of magnitude of the electrostatic force compared to the gravitational force. If I added them together, I'm still just going to get the value for the electrostatic force. Because gravitational is so small, it makes no difference.
I got 4.6 times 10 to the minus 18. Oh, no, wait. Oh, yeah, sorry.
So which one's correct? Did someone type it in wrong? Is that right, yeah? Okay. So now we're going to do part C. Now, remember I said I'm not going to give you the exact value for the diameter of the atom. We're just going to estimate it. So these values we just calculated are sort of ballpark figures. However, if we find the ratio between them is not going to be a ballpark figure. It's actually going to give us the ratio between how strong a electrostatic force is compared to the gravitational force within an atom. So for part C, we're doing Fe divided by Fg. So we've got 4.1 times 10 to the minus 47 on the bottom. And our value for Fe was 9.2 times 10 to the minus 8. Now if you put that into your calculator, what do you get?
9.8.
I think it was 9, was it 9.2 or 9.8? 9.2. So what does that give us?
2.2 times 10 to the 39.
2.2 times 10 to the 39. So the electrostatic force is 10 to the 39 times bigger than Fg. So on small scales like this, gravitational forces are negligible compared to any other force. And that's the end of 7.3.1.